Hi guys. Okay, so now we're going to do a pure A2 pure paper, pure 3. We're going to get through as much as possible in the next hour, but we might have to skip a few questions. So I'm going to try and go through it quite quickly. First question. All right, they've given us an equation asking us to solve for x. This is pretty straightforward. You take this over, you end up getting an expression for 3 to the x is equal to blah, and then x has got to equal to the log base 3 of blah. Really not much to it. Okay, so the next question is requires some knowledge about the Taylor series. They need you to expand this guy. They're asking you to expand the whole function, but this guy doesn't need to be expanded. So once you've expanded him, you just multiply him by him, and you get the whole thing. So our function that we're looking to expand is f of x is 1 plus 2x to the minus 3 halves. Well, differentiate it once, evaluate it at 0, differentiate it twice, and evaluate that at 0. You will get an expansion up to terms x squared. You then multiply that by the 2 minus x, and that'll give you your series. You remember, you can ignore any higher terms than x squared. And that's full marks in the bag for you. So just remember, expand means Taylor expansion, which will always be actually a Maclaurin expansion because it's around 0. That's this thing you're evaluating at. Sometimes you might see something that's to an integer, a positive integer power, like 3 or something, in which case you can use the binomial expansion, and this thing will have an exact answer if it can be expanded with the binomial expansion. This is exact, by which I mean you can get a finite number of terms. You know, obviously it's a cubic thing cubed. You know how to do that. It's a finite number of terms and it's an exact expression. A Taylor expansion does not give you an exact expression for this function, because an exact expression would require all of the terms going to infinity, and we don't really have time in this exam for that. So instead, it's an approximation that's better and better the more terms you add. They're only asking you for terms up to x squared, so you got no problem. Okay, question 3. This thing is just mucking around with the proving this identity is mucking around with the trigonometric identities. So we have that sec theta, which is 1 over cosine theta, is equal to those. So if we multiply both sides by cosine theta, we get 1 is equal to 3 cosine squared theta, which is 1 minus sine squared theta. Plus, well, this is sine over cosine, and we're multiplying by cosine. This is sine theta. And this gives us an expression for sine theta. In fact, it's a quadratic equation. So we get that sine of theta is equal to 1, or sine of theta is equal to minus 2/3. But we're not done. We're given a range in which to talk about this. So if I draw a tiny, tiny little sine function between, maybe we can zoom in my more space. Okay, so if I draw some axes, and I have a sine function between, so the sine one kind of looks like that. So that's 2 pi. This is pi over 2, which is 90 degrees. Minus pi over 2. Well, what's it doing down there? It's just curving down to a maximum again and going on. So this is our range that we're allowed to look in, and it's strict. So it does not include these points. These are empty. So we're looking for some value of theta, which will give a value of sine theta of the y-axis, of the function, which is either 1 or minus 2/3. Well, where is sine theta equal to 1? It's equal to minus 1 here. It's equal to plus 1 here, but only at the point pi over 2 at 90 degrees, which is not included. As you see, revealed, these are just less than, it's not less than or equal to. So the sine of theta is equal to 1 value of the quadratic equation is just not allowed. We can have minus 2/3, maybe somewhere there. So we're allowed that value. And that'll give us minus 2/3, which is within the range that they've given us. So all you do is find the primary value, sine minus 2/3. And it'll give you some primary value of theta. Now you can check for alternative values, like additional values, but actually there are no other values of theta within this range that will give you minus 2/3. So you're done. Okay. Ooh. Okay, so this is just differentiation for number 4. So we've got this equation for a curve, and basically they're asking us to implicitly differentiate. Or another way you can think of it is just you take the equation and you differentiate everything with respect to x. So let's just, is that the smallest we can go? Maybe a little slower? No. All right. So let's apply the operator d dx to the left-hand side. Well, this is d dx of xy. This is the way I'm doing it. There's a bunch of ways you can do it, but they all lead to the same answer. So I'm going to picture this as two functions multiplied together. Well, I know the product rule. This is going to be d dx of the first function, xy, times the second function, plus the first function times d dx of the second function. Well, what's this? d dx of xy, this again is a product of two things. So d dx of x is just 1, plus, so this is another function, x and y. So it will be d dx of x times y is y, plus x d dx of y, which is just dy dx, times x minus 6y, plus xy. And then again, I differentiate this respect to x. The first thing just becomes 1. And this is minus 6 dy dx. Right, well, that looks exhausting. But they're asking for the point on the curve at which the tangent, so there's something drawn with the same gradient, is parallel to the x-axis. Well, being parallel to the x-axis means that dy dx, first derivative, is 0. So we can just happily get rid of that guy and that guy. So that leaves us with y, if you work it out, no problem, 3y minus x is equal to 0. So either y is equal to 0 or y is equal to x over 3. But you have to be careful here. Remember that they're given us a clue, and they've said show that there is only one value. Well, one of these must be bust, right? Well, if you notice, if you plug y is equal to 0 into this initial equation, this gives the whole thing is 0. So you get that 0 is equal to 9a cubed, or a is equal to 0. But we're told that a is a non-zero constant. So this is a contradiction, and that value cannot be right. So y is equal to x over 3 is the only one which works. So let's return to our original equation and plug in y is equal to x over 3. We get that x squared over 3, so it's the original equation, x squared over 3 times x minus 2x is equal to 9a cubed. If we solve this for x, we get x is equal to minus 3a. Minus 3a. So therefore y is equal to minus a. So that is the point. The point is minus 3a, a. And that is the only point at which this is true. Okay, number 5. Well, again, we are mucking about with identities. So because I haven't got much space right now, I'm going to just write tan 2 theta is t2 theta, tan theta is t theta, and so on. So first we want to get rid of this 2 theta. So remember, we're looking at the left-hand side. So let me scrub so I've got some more space. So let's say left-hand side is equal to tan 2 theta minus tan theta. Well, first of all, I want to make this tan 2 theta into something with just tan thetas. So I'm going to express that. It's in your formula booklet. 2 tan theta over 1 minus tan squared theta minus tan theta. Now I'm going to pull this tan theta over this denominator and then extract a common factor of tan theta. This becomes tan theta times 1 plus tan squared theta over 1 minus tan squared theta. And you can recognize that tan is equal to the sine over the cosine. So if I multiply top and bottom by the cosine, I get that tan theta if I multiply top and bottom by cosine squared plus sine squared over cosine squared minus sine squared. You'll recognize that cosine squared plus sine squared is 1, and that this thing on the bottom is the cosine of 2 theta. 1 over the cosine 2 theta is sec 2 theta, and there we go. Tan theta times sec theta, 2 theta. Right, now they're asking us to apply this. So we need to show that the integral of this business, which is equal to this business, is blah. So this is not conceptually difficult, but can be a little finicky. I'm going to try and find some space to do it. So what was this? Question 5.2. 5 subsection 2. So we have the integral, and I'm going to just put in the left-hand side rather than the right, because we always like to split things up in integrals, always makes it easier. Tan 2 theta minus tan theta d theta. So this can be separated into two different integrals, because integration is linear in that way. Now in the first one, I'm going to change variables. So I'm going to change variables for the very first one to 2 theta. So I want something that's like d2 theta. Well, d of 2 theta is just 2 d theta. So d theta is 1/2 d2 theta. And you'll see what I mean by, if you have experience switching variables, but this is a fairly mundane one. This will give this 1/2 integral from 0 to 2 theta will be pi over 3 tan 2 theta d2 theta minus, and we won't change the other ones, tan theta 0 to pi over 6 d theta. Okay, so you see why I've done this now. Now essentially 2 theta is x, a dx, and this is the value of x. So it just makes it easier because I know the integration for the tangent. So yeah, the integral should be in your formula notebook of theta is natural log of 1 over cosine of theta. So I'm just going to call both integration variables x. Remember, integration variables, like that, you can call them anything within the limits of integration because they're all kind of summed over. So I'm going to call them x. So we've got that 1/2. So this integral is equal to 1/2 times the natural log of 1 over cos x, where x is 2 theta, between 0 and pi over 3, minus the natural log, oh, absolute value, by the way, just be sure of that, 1 over cos of x between, where x here is theta, between 0 and pi over 6. Well, we remember from our special triangles, well, what is, so pi over 3, well, in degrees, that's 180 over 3, which is 60, and pi over 6 is 30. So the cosine of pi over 3, and this is the 1, 2, square root 3 triangle, cosine of pi over 3 is going to give us 1/2, and here it's going to give us 1 over square root 3. No, it's that one. Sorry. Sorry. Square root 3 over 2. Going nuts. It's because 1 over cosine, so I'm confused. Okay. So in this case, we have, let's evaluate it, 1/2 times the natural log of 1 over 1/2, absolute value, which is just, natural log of 2, minus the natural log of 1 divided by the cosine of 0, which is 1. It's the natural log of 1, which is 0. Minus the natural log of the absolute value, but let's throw that away because we haven't got any minuses here, 2 over square root 3 plus natural log of 1, again, is equal to 0. So we've got 1/2 natural log of 2 minus, and let's basically square this, and we get minus 1/2 natural log of 4/3, because remember, we can just take the half up here, it's going to square root this thing inside, give us 2 over square root 3, which is 1/2 rules of logarithms, natural log of 2 over 4/3, which finally gives us 1/2 natural log of 3/2 as required. So that just gets a little bit finicky with the limits and everything, but I don't think it's too hard. Just easy to make really like simple mistakes. I'm gonna make this smaller. Oh, beautiful. I've got more space. There might have been a pi or something lost there. Let's put you back. Right, so that was 5, 5, 2. Okay, question 6. Cosec of 1/2 of x is equal to 1/3 x plus 1. So this is one of those where you've got an x on both sides, and you can't really like undo this cosec function while this x is still here. It's not really, you can't solve it analytically. What you can do is solve it numerically, which means sort of iterate through a procedure and get closer and closer to the value until you're so close you don't really mind that you're not exact. So in the first question, they're asking you to sketch something. So you're not asked to calculate anything yet. Let's think you may have the graph of cosec memorized. Good for you. Otherwise, a quick way to derive it in an exam is consider the inverse, not the inverse, but the 1 over cosec, which is obviously sine. So the sine of x over 2, the graph for that, well, if this is x, normally, so if x is equal to 2 pi, sine is equal to pi. So here's 2 pi. So this will be the sine of pi, which is normally halfway between what it should be. So anyway, the thing reduces the period, increases the period by 2, because it takes an extra 2 times as much x to get the same value of sine. So there's pi, or 90 degrees. 180 degrees. That's 90 degrees. And so let's consider 1 over the sine of x over 2. And you can see here that at x equals 0, this thing is sine of is 0. So this thing blows up around here. But then it comes down again, and it blows up again here. So wherever sine of x is 0, 1 over the sine of x is 1 over 0, which goes to infinity. Here, it's at 1 at pi, so it's 1 over 1. So it reaches 1 here, and then goes back up to infinity. And we don't care about what happens over here, but blah, blah. You may recognize this. So this is the graph that we want, the cosec of x. And the other line, the thing we're saying, we're equating, is y is equal to 1/3 x plus 1. And that is probably very simple. At x is equal to 0, y is equal to 1, so it hits there, it's the y-intercept, and then it crosses x, crosses the line there. And now we only care about up until pi, right? So it only crosses once, and that's your argument. Because there's only one crossing, because the next crossing is over into this sector. And that's all you need to show, because it's only asking you to sketch it. So the next one is asking you to calculate it. And again, it can't be solved analytically, so we have to use numerical methods. So the way you do this is you're only trying to show that it's between these two values, right? So you don't have to sit there until the next question and crunch through a real iterative method. But you do have to show that it lies between these two. So your first plan of attack is obviously going to be to evaluate these two sides at each of these values. So it's at 1.4. So let's say x is equal to 1.4. The cosec of x over 2, you can just do in your calculator, is 1.552. And 1/3 x plus 1 is 1.467. So we can see that it's not perfect. Let's try x is equal to 1.6. This is not the cos, sorry, cosec, not the cosine. This gives us that the cosec of x over 2 is 1.394, and 1/3 x plus 1 is 1.533. Now, this is not great either, but you'll notice that for this point, the x equals 1.4, the cosec curve is above the line, the linear curve. And here, cosec is below the line. Well, in that case, it must have crossed the line in between those 2 points. These two, to reverse position, here cosec is above, and here it's below. They must have crossed between those two values, and that is your argument. Okay, the next question is a little odd, really, but the argument, what they're trying to say, is that here's an iterative formula. Prove that this is the right, a good iterative formula to get to this, the solution to this problem. So basically, in a good iterative formula, one that converges, you will get, any converging formula will eventually have that xn, n plus 1 is equal to xn. So each time you crunch through this again, it doesn't actually change. Each subsequent value, it converges to a single value and then stays there. So that is what converges means. So let's do that. Let's set xn is equal to xn plus 1, which is equal to 2 arcsine of 3 over xn plus 3. And you'll find that if you rearrange this, you get this equation. So that's all that they're requiring. The argument is, if it converges, then this is true. If that is true, then that is true. And so it is an iterative formula for that equation. Finally, they're asking us to actually iterate it. So this is the same way we've done it before. You have your xn, and let's use 1.4, and they say 3 decimal places, so there they go. That gives us the next xn plus 1. Yeah, should be 1.5. Then that, if we type it into our calculator, gives us 1.45946. Oh yeah, this should give 5 decimal places. I can't remember. I think that was not quite accurate. But anyway, it crunches along like this. 47578, blah, blah, blah. And eventually you get, if you keep plugging these in as the solutions of xn to find xn plus 1, and they just like trail along, then you'll end up 1.47119, and the next one will be 1.47101, and at that point you're happy with 1.471. You think those are pretty reliable, those first 3 digits, because they're not changing anymore. And that's the essence of this iteration, if it converges. All right. So we're given this curve, and they want us to find, firstly, the x-coordinate of this maximum. Well, we know how to find a maximum. We differentiate. So dy dx is, remember, product rule, 2 minus 2x, differentiating the first function, and then leaving the second function alone, e to the 1/2 x, plus, let's differentiate this one instead, 1/2 e to the 1/2 x times, and leave the other one alone, 2x minus x squared. So for m, at m, dy dx, i.e. the slope, is equal to 0. So we end up with e to the 1/2 x. So let's multiply everything by 2. 4 minus, okay, let's not confuse things. 2 minus 2x plus 1/2 2x minus x squared is equal to 0. Now, this thing can never equal 0. E to the 0 is 1. You can never make anything raised to the, you can't make a number raised to a power be equal to 0. There is no way. So therefore, this is the thing that must equal 0, the second part. So let's multiply that by 2. We get 4 minus 4x plus 2x minus x squared is equal to 0. And this gives us 2 values of x. 1 minus 1 plus or minus the square root of 5. Now we notice that minus 1 minus the square root of 5, well, that's less than 0, obviously. And our curve only sits sits here. M is definitely positive. So we know that x, m, the x coordinate of m must be -1 plus the square root of 5. So that's within the interval shown. That's the only value of x that works. Now they want the area of the shaded region bounded by the curve and the positive x-axis. So this just requires you to know that the area under a curve is the integral of that curve. So let's go through it. Luckily, this is a very nice one where it's just bounded by the x-axis, so you don't have to worry about, getting like that area or anything like that. And subtracting, you just have to integrate this this curve. Well, we'll see how simple it is. So we're looking for the integral from 0 to 2. Those are our x values because we're integrating over x, of 2x minus x squared e to the 1/2 x dx. Well, it looks horrible, but it also looks like a perfect ground for applying integration by parts. So remember, you just pick your the integration by parts formula, or the way I always remember it, super simple. Integral of fg prime is equal to fg minus integral of f prime g. Now, you always look for the thing which is easiest to integrate, to designate as your g, because you see that g appears integrated here, because it was g prime, and now you've integrated it to get g. So we're looking for something here which is easily integrated, so we can set it to be our g prime and then have it integrated on the other side. Well, the exponential function is super easy to integrate. It's probably the easiest thing. So let's set that as our g prime and that as our f. So therefore, g must equal the integral of e to the 1/2 x, which is just 2 e to the 1/2 x. Beautiful. So this thing, it's going to be equal to, remember, even with integration by parts, you still have to evaluate this thing between the limits. F, 2x minus x squared, times g, 2 e to the 1/2 x, evaluated between 0 and 2, minus integral of f prime, so this thing differentiated, which is 2 minus 2x, times again g, 2 e to the 1/2 x dx. So this is pretty straightforward to evaluate. In fact, you get 0 because it's 2 times 2 minus 2 squared is 0, and the other limit is 0. This is all 0. Minus 4, so we're going to multiply this out, times the integral of e to the 1/2 x plus 4x, integral 4 times the integral of x e to the 1/2 x dx. So this thing again, e to the 1/2 x, will be very easy to integrate. I'm sure you'll have no problem doing that. This thing just needs to be integrated by parts once more. And that's it's exactly the same procedure. So you should end up with 24 minus 8 times e, i.e. e to the 1, e just being a number. All right, number 8. Two planes have these equations. Show that the planes are perpendicular. Well, usually when we see a, show that these things are perpendicular question, we're used to seeing vectors. Whereas these are kind of the equations that the planes are obeying. But there's a very easy way to extract the vector that's normal to the plane from one of these equations. In fact, it's just the coefficients of the x, y, and z. So the normal to this plane is 3, 1, minus 1, and the normal to that plane is 1, minus 1, 2. Now, I would like to just show you why this works. So let's see if this, I've got a beautiful blank page down here. So this is question 8.1, background information, just for your edification. So let's look at that first equation. 3x plus y minus z is equal to 2. That was it, right? Yes. So we can also think of this as a dot product between 3, 1, minus 1, and a vector x, y, z, which is equal to 2. So this is a dot product, a scalar product. So obviously it gives a scalar. So this is any vector which is on the plane, x, y, z, some general coordinates. Let's call this A. Or no, let's call it N, suggestively. So we have that N dot V is equal to 2 for all V on the plane. So all points that, actually let's call it P, because V implies that the vector is going along the plane, which it isn't. The P is the vector from the origin to some point in the plane, not from the plane at one point in the plane to another. So let's consider N dot, this is P. I wish I would stop doing that. N dot P is equal to 2. I don't know what that is. Okay, so let's consider the vector P minus Q, where P and Q are both points on the plane. Well, P minus Q is a vector from Q to P. And if Q and P are both on the plane, then this is a vector along the plane, because you're getting from one point on the plane to another, then this must be a vector along the plane. So let's consider N dot QP. So we're dotting this N with, that was just found in our definition, with a vector which is along the plane. Well, that's N dot P minus Q, which is N dot P minus N dot Q. Well, these are both points on the plane. So N dotted with either of them is going to be equal to 2. So it's 2 minus 2, which is equal to 0. Therefore, N must be perpendicular to all. It's perpendicular to P for all P on the plane. So therefore, N must be the normal vector to the plane because it's perpendicular to all points. Sorry, I just realized I expressed that badly. It's not perpendicular to P. It's perpendicular to the plane, which is given by P minus Q. Perpendicular to the plane. P is just to clarify, that's the origin. Here's our plane. Here's N, all nice and normal. So it's perpendicular to this vector, but it's not perpendicular to the position vector P. That's not going to be 90 degrees between those guys because that's coming from up here, but it is perpendicular to the plane. Right. So now we know the perpendicular, the normal vectors to either of these. Well, if two planes are perpendicular, that means that their normal vectors are perpendicular. So if we have plane 1 with N1 and some other plane 2, which has a right angle between them, well, obviously, this one is going to be a right angle between those two guys as well. So we just have to dot them together. So we have 3, 1, minus 1, dotted with 1, minus 1, 2, and you find this is equal to 0. Now they want a vector equation for the line of intersection of the two planes. So there's obviously going to be a line. If you think of two planes intersecting, there's going to be a sort of like a thin line between them. Now, planes have 2 degrees of freedom. They have like 2 independent ways in which you can move. A line only has 1. You can move up and down the line. You can't strike off to the side and stay on the line. So so we can express this by looking at the equations of the plane, and you do it in the usual way. We'll solve for z and then set them equal to each other. So I'll do it down on the next page. I think this was 2. So plane number 1, we had that z is equal to 3x plus y minus 2. And for plane 2, we had that z is equal to 1/2, 3, I don't know what's up with this graphics tablet, 3 minus x plus y. We set those equal to each other. We will get that y is equal to minus 7x plus 7. So this is the relationship between y and x in our line that are obeyed. But that doesn't mean that the line doesn't move in the z direction. From like a 3D perspective, the z coordinate does change. So we need to find out what that is. So z in terms of x is, we just plug it back in, we get minus 4x plus 5. So you see that this has 1 degree of freedom in the sense that once you've decided x, y and z are completely determined. You only have the freedom to choose x. Then y and z are defined for you. So that's what we mean by degrees of freedom. And that's equivalent to moving up and down the line. So what they want is a vector equation of the line. So for a vector equation of a line, what we need is a point on the line and a point parallel, a vector parallel to the line. So that'll get us onto the line and then moving up and down it. You should recognize that kind of equation. So for this, I'm just going to extract 2 points on the line, and then I have all I need. So let's say I consider the point where x is equal to 0. So then y would be equal to 7, and z would be equal to 5. And I also consider the point where x is equal to 1, and then y is equal to 0, and z is equal to 1. And this is all I need. So some vector v, which goes along this line, is going to be equal to this one minus this one. Remember, if I take the coordinates of this line and subtract the coordinates of that line, I'm getting a line that goes like that. And that's parallel to the line. Yeah, if you're using the word line too much. So I'm going to go this one, subtracting that one. 1 minus 7 minus 4. No problem. I don't have to normalize it. I don't have to, I don't have to make it a unit vector. I don't have to do anything else to it. This is a vector that is parallel to the line, so it's good enough. So here is my equation for the line. I need to get on the line, 1, 0, 1, plus lambda, being some parameter, 1 minus 7 minus 4. And that's it. I get on the line and then I move up and down parallel to it. Okay, so I'm going to speed up because we're really almost towards the end. They want us to solve this equation for a complex number w. Well, this is actually not so bad. You will solve it using the quadratic equation. You're perfectly allowed to do that, the formula, sorry. And you will end up with w is equal to minus 2 over 5, 1 minus 2i, plus or minus 3/5, 1 minus 2i. The only things you might need to be aware of, or might help, is that if I have something over, so if I have 1 over 1 plus 2i, I don't like having imaginary stuff on the bottom, or complex stuff on the bottom. So what I do is I multiply this by the complex conjugate divided by itself of this thing on the bottom. So this is perfectly allowed because this is just 1. So this thing is equal to this thing times that thing. Well, that allows me, on the top I just have 1 minus 2i. It's on the top, so I'm fine with that. And then this thing, well, it's just something times its own complex conjugate. So it's just the real part squared plus the imaginary part squared. So you need to do that a few times when working this out. So I have 2 values of I here. I really don't know why it does that. Three over 5. So I have two values of I. And yeah, there's really, you get a W plus, which is 1 over 5 minus 2/5 I, and you'll get a W minus, which is minus 1 plus 2I. Right, so the next one's a little trickier, but let's have a go. So on a sketch of an Argand diagram, shade the region whose points represent complex numbers satisfying these two bits. So really forget about the actual inequalities until the end. Just think of as if this was an inequality, and then draw that curve. So z minus 1 minus I is equal to 2 is going to be the edges of the space we're allowed to. Well, this is modulus, and this is a complex number. So I'm going to just express this first as x minus 1 plus I y minus 1 is equal to 2, absolute value, because I'm just saying that x is equal to z is equal to x plus iy. Often that can that's just the best way to go. Even if it takes a little longer, it's much less prone to mistakes than if you try and work with z. So this is modulus. I'm just going to square both sides. So that gives me that x minus 1 squared plus y minus 1 squared is equal to 4. Because remember, x plus iy mod squared is x squared plus y squared, because what it actually means is x plus iy, x minus iy, and I squared is minus 1. So we have this, but before we could multiply it out, but that would be a mistake, because here what we have is the equation of a circle with center at 1, 1 and radius 2. Well, that's what we need. We need to draw our Argand plane. 1, 1. I know you might be tempted to write I here, you can, but really strictly the Argand plane, this is the imaginary part of some complex number z, and this is the real part of some complex number z. And the imaginary part of this z, or say x plus iy, is y, not iy. So you sort of extract the thing that's next to the I. So really this is 1. But it's but this point would be represented by 1 plus I. So little subtleties of the Argand plane, I guess a little confusing. Anyway, so that's the center. And we have 2, a radius of 2. Actually, I don't have enough space. It's going to be something awful like that. You'll do a much better job. Oh my God. Oh, that's really terrible. Okay. It doesn't help that the graphics tablet is spazzing out, but anyway. Okay, there's our radius 2 circle centered on one eye. And the next part tells us that the argument of complex numbers must be between pi over 4 and minus pi over 4. Well, the argument is just the angle, obviously. And pi over 4 is 45 degrees. So that would be the upper limit. That would be the lower limit. And this is the allowed area. And that's all they ask for this question, is just sketching. Okay, very last question. I think we've got enough time. This is a differential equation question. And what advice to give you? Oh yeah, so this is, the first part is a little bit tricky. So you got dx dt. Let's just fence this off. Okay, you got the dx dt is equal to kx 4 minus x. So we separate variables as usual. And we get that dx over x 4 minus x is equal to k dt. But this thing doesn't look very easy to integrate, you know, once we start integrating. How do we do this bottom one? Well, we just use fractional decomposition. So 1 over x 4 minus x is equal to a over x plus b over 4 minus x. If you solve this, you'll find that a and b are equal to 1 over 4. So really, our integral, so on this side, we're integrating from 0 to t. So we get that kt, and the right-hand side is the integral. The right-hand side is the integral of 1 over 4x plus 1 over 4 minus x dx, which is just going to be equal to, let's take the quarter out, quarter natural log of x plus, oh, actually minus the natural log of 4 minus x, and evaluated between the same limits, so 0 and 2. They've given us the boundary conditions. Sorry. The boundary conditions we should be using, they're being a bit tricky, is 0.4 and 2. And this thing should be evaluated between 0 and 2, so you get 2k. And this will, once you evaluate that, that'll give you that k is equal to 1 over 4 natural log of 3. Second part, really exactly identical situation. You have, so 90% of the total land area is 3.6 square kilometers, what they've given you. So you get that 1 over 4 natural log of x minus, or let's pull those logs together and go natural log of x over 4 minus x by the rules of logarithms, evaluate between 0.4, so at time equals 0, it was 0.4, to 3.6 is equal to 1 over 4, this is our value of k, natural log 3, times the time, evaluate between 0 and the t that we want to find. So this gives us, we cancel the 1/4, we get the natural log of 9 minus the natural log of 1 over 9, which is equal to 2 times the natural log of 9, because this is 9 to the minus 1, and the minus 1 comes outside, which is equal to 4 natural log of 3, and all of this is always equal to natural log of 3t. So therefore t is equal to 4 years. And we are done, just in time. I hope that wasn't too quick. Please, if you have any questions, please post them on the Slack groups, and I'll do my best to answer them in time. Good luck.